everyone and welcome back to Data Squash. In today's video, we'll be talking about cross-validation. What is cross-validation and why do we need it? So before we talk about cross-validation, let's back up a little bit. When a data scientist wants to fit a model to the data, they need to make sure that the model actually works and provide accurate results. So they do predictions using this model, and they calculate the error of the model, which is basically how far are the predicted values from the true values. And this whole process is called validation. But what happens if you use the same data that you fitted the model on in validation? Well, if you are using the training data to calculate the error, then the error will be deeply underestimated. Why, you may ask? Because the model is being validated by data that it has already seen and been trained on. So it's more likely to do a good job in making predictions and less likely to make errors. Therefore, when a data scientist wants to do validation, they take out a part of the data that they don't include when training the model, and they test the model on this set. We call this the validation set. So as we can see here, we have the whole data set, and we randomly split it into a training set and a validation set. The training set we use to fit the model, and the validation set we use to test the model and calculate the test error. A general ratio for splitting is 70% for training and 30% for validation, or 80 to 20. And these are the most frequently used ratios, but basically you can use any other ratio you want. So do you spot a problem with this approach? I'll give you 1 minute to think. Just kidding, we don't have time. So the problem with this approach is that we don't use the whole data for training. As you can see here, we're taking a bit of it apart, a proportion. And this is an issue, especially when the size of our data is very small. So we want our model to see as many examples, as many observations, so it would be able to generalize better to new observations that it hasn't seen before. Also, another problem is that the results we get from doing this split depends a lot on which observations are used for training and which are used for validation. I got this graph from the book called ISLR. It's a really nice book and I'll link it down below. In this, we have on the x-axis the fitted model. So we have 1 degree polynomial, which is basically linear regression, compared to a higher order of degrees polynomials. And as we go to the right, as we increase the degree, we're basically increasing the complexity of the model. On the y-axis, we have the mean squared error. And these lines that we have here, for each line, we have a data set. So it's a data set of 392 observations, and a 50-50 split was made. Each line here is a different 50-50 split. So it's a random split, and each line there's random observations that have been allocated to the training set and randomly allocated observations to the validation set. And as we can see here, we can notice something really interesting is that for each line, for each 50-50 split, we get a whole different range of mean squared error. So as we can see for the yellow line here, it's a very low mean squared error over all the different models that we have fitted. But when we go up here, we can see for the orange lines, there is a way higher range of mean squared error for all the different models that we used. And this is another important thing that we might consider here is that actually the allocation of observations into the training and validation sets cause a high variability in the mean squared error, which is something that we really don't want to happen because it's inaccurate, right? So if I'm a data scientist and I made this split here using the orange line, then I might get a very high overestimated mean squared error, and I might think there's a problem with my model. And also, another data scientist could fit the 50-50 split of the yellow line here, and they would get a very low mean squared error, and they would think that, oh, like they're doing a really good job. It's very inaccurate. And that's why we need cross-validation.